Welcome back. In this section, we'll be talking about graphs of exponential functions. So we'll begin with the basic shape for our exponential functions, and then of course we'll do some graphing using transformations. A couple of things just to remind ourselves. Number one, that when we're talking about an exponential function, the base needs to be positive. So here a is something that is larger than 0. And as it turns out, there are two basic shapes for this exponential function, depending on whether your base is larger than 1 or if your base is between 0 and 1. If you have a base that's between 0 and 1, this is something where your graph is always decreasing. Remember that increasing versus decreasing, an increasing graph is one where as we look from left to right, the y values are going up. A decreasing graph would be one that as we look from left to right, the y values are going down. So if we happen to have a base that's between 0 and 1, your graph will always be decreasing. We would call that exponential decay. The other kind of graph would be when a is larger than 1, and if that's the case, your graph will always be increasing, and that is exponential growth. So the two basic shapes that we have are this. If you have your graph of a to the x and the base a is larger than 1, then it's an increasing graph. It's always going upwards as we move from left to right. And if a is between 0 and 1, then it's always a decreasing graph. Notice that these are essentially mirror images of each other, mirror images in that y-axis. So one of them happens to be curving upwards, and the other one happens to be curving downward. Some things that are true for all of these graphs would be that, number one, you'll notice that the domain for both is all real numbers. You can put in whatever value of x. There's a graph everywhere from the far left to the far right. So the domain is all real numbers. But if you're also looking at this, you'll notice that we are always above the x-axis. In other words, the range is things that are larger than 0. And that's true whether your base is a small number or a large number. Since a is always going to be positive, then positive number to any power will always be positive. You'll never have a value of a to the power of x that is either 0 or below 0. And actually that tells you one further fact. Since a to the power of x always needs to be positive, always needs to be larger than 0, then it will never be equal to 0. You will never cross that x-axis. This exponential function, a to the power of x, for any base, will have no x-intercepts. You also have 3 points that are on all of the graphs for the exponential functions, no matter what the base is. They all have the y-intercept 0, 1. Whether the base is small or large doesn't really matter. They all pass through the point 1, a, where a is whatever the base is. So if this is a graph where a is larger than 1, then a is something that's larger than 1. That's an increasing graph. If a is less than 1, between 1 and 0, then that's something where you have a decreasing graph. But the point 1a would be on both graphs. And similarly, the point -1, 1 over a is on both of these graphs as well. So we've got some points that are in common on all of our graphs for exponential functions. So actually the way that I think of it myself is, instead of thinking of the two basic shapes, I think about these 3 points. Once you plot the 3 points, then you'll know whether the graph is trending upward or trending downward. You'd be able to tell whether it's an increasing or a decreasing graph. One other thing that we have here, which I haven't indicated on the graph itself, but I will when I do graphing by hand, which is that both of these have a horizontal asymptote. You'll notice that this is an example of a graph where the horizontal asymptote really only applies to one side of the graph. That for the exponential function on one side of the graph, it is tapering off to that horizontal line y equals 0, and on the other side it's heading upwards. And the same thing is true for the other exponential graph. On one side you have that horizontal asymptote that we're trailing off to, and on the other side we're heading upward. So this is an example of a graph where, yes, we have asymptotes, but also the horizontal asymptote only affects one side of the graph, because on the other side of the graph it heads upwards. Okay, so we are going to graph this function y equals 3 times 2 to the power of x minus 1 minus 2. And so the first thing that I'll do is I'll start off with my basic function y is equal to 2 to the power of x. If we're thinking about our transformations, the transformation here, the minus 1, the one that's being subtracted from x, that's telling us that we're going to the right by 1. That's a horizontal shift. We have a vertical stretch by a factor of 3. And we also have a vertical shift, and this would be a shift of going down by 2. I know that both of those, the vertical stretch of 3, it's a vertical stretch because the entire function is being multiplied by 3. The minus 2 at the end, that's a vertical shift because the entire function is having 2 subtracted from it. So I'm actually going to do 4 graphs here. The basic graph of 2 to the x, then shift it to the right by 1, then do a vertical stretch, then go down by 2. So to start with my first one, if I'm looking at the graph of 2 to the power of x, I know 3 good points. It passes through 0, 1. It passes through 1, comma, whatever the base is, and here the base is 2. So we have the point 1, 2. It passes through negative 1, comma, 1 over the base. Since the base is 2, then 1 over the base would be a half. So we have the point negative 1, 1 half. I also know that I'm going to have that horizontal asymptote of y equals 0. You can draw it on both sides of the graph if you want, but I only bother drawing it on the side of the graph where the line actually comes into play, which is, for this graph, would be on the left side. I can see from my 3 points here that my graph should be curving upwards. This is exponential growth happening here, and then trailing off to the horizontal asymptote. And I'm just going to make these points look a little bit more obvious. There we go. Those are my 3 points. And then I need to label my horizontal asymptote. There we go, y equals 0. And then now label my equation itself 2 to the power of x. All right, so I've got my first graph done. Next graph, we're going to take this and shift everybody 1 to the right. So we're taking all of our 3 points that we had and moving them 1 to the right. So the point 1, 2 becomes the point 2, 2. The point 0, 1 becomes the point 1, 1. The point negative 1, comma, a half becomes the point 0, 1 half. And I still have my horizontal asymptote. And the general shape of the graph is still the same. Exponential growth is happening here. There we go, tapering off to that horizontal asymptote. Good, good, good. And I'm just going to fix this and make this look a little bit nicer. So labeling that point again, that is 0 and a half. There we go. And now I'll just label my equation. This would be y is equal to 2 to the power of x minus 1. Okay, so now the next thing that we'll be doing will be taking care of our vertical stretch. Our vertical stretch is a stretch with a factor of 3. So that means we're going to be multiplying all of our y values by 3. So if we're thinking about the y values that we have here, we'll multiply 2 by 3, the 1 by 3, and the 1/2 by 3. If we're thinking about things that would affect the horizontal asymptote, you'll notice that our first move that we didn't affect the horizontal asymptote, and that's because if you take this horizontal asymptote and shift it to the left or shift it to the right, it's a horizontal line still of y equals 0. Shift that line to the left, it's still y equals 0. The only thing that will change the location of our horizontal asymptote will actually be when we shift our graph up or down. When we shift our graph up or down, that horizontal line will be shifted up or down along with it. So right now, with our vertical stretch, with our horizontal shift, that horizontal asymptote hasn't moved yet, but just beware that it will move eventually. Okay, so let's do the next part, the multiplying everybody by 3. So the y coordinates are all being multiplied by 3 here. We had the point 2, 2, and when we multiply the y coordinate by 3, we get 2, 6. We had 1, 1. When we multiply the y coordinate by 3, we get 1, 3. We had a 0, 1/2. When we multiply the y coordinate by 3, we get 0, 3/2. So we have our points 0, 3/2. We have the point 1, 3, and the point 2, 6. Our horizontal asymptote will still be here on the line y equals 0. And the general shape of our graph is still the same. It's still exponential growth. And it's still going to be tapering off to that horizontal asymptote on the left. We've just stretched our graph vertically. That's all we've done here. That is 3 times 2 to the power of x minus 1. And there we go. We've got our second transformation done. And then our last transformation that we have to do, if we flash back, remember that the last transformation here was a vertical shift, and it was a vertical shift downward by 2. So that means that we're going to now transform our graph by subtracting 2 from every y value, but that also means that this horizontal asymptote will be shifted downward by 2 as well. So that means that if we're thinking about our graph here, instead of having a horizontal asymptote of y equals 0, we will have a horizontal asymptote y equals -2. And now let's start putting in our points. We had the point 2, 6, and that was being shifted downward by 2. That would be now the point 2, 4. We had the point 1, 3, shifted downward by 2. That's now the point 1, 1. And then we had the point 0, 3/2. 3/2 shifting it downward by 2, or subtracting 2 from 3/2. That's -1/2. So our third point would be 0, -1/2. And now we will draw our curve. Again, tapering off to that horizontal asymptote. And there is our graph of y is equal to 3 times 2 to the power of x minus 1 minus 2. And there was one last part of this problem, just to finish off here, which at the beginning of things we had asked, what is the domain and range of this function? And I can address this now, but I could have actually addressed it in advance. I know that for any exponential function, the domain is all real numbers. So that part was the easy one. We know for any exponential graph, any x value is fine to use. And as far as the range goes, I mean, if I'm looking at my last picture, I can see that since I have that horizontal asymptote of -2, that I'm only getting y values that are larger than -2. We could have probably figured that out, though, from the original properties that we knew that for any exponential graph, the range of a to the power of x is just positive y values. So we know that our basic shape starts out with only positive y values. And we know that we were going to take this whole graph and shift it downward by 2, which meant that not only were we going to get y values that are larger than 0, actually we are now going to get y values that are larger than -2. So my domain, all real numbers, my range, things that are larger than -2. All right, I want to use transformations to graph this exponential function, 2 minus e to the power of x over 3. And I'm going to rewrite this to make the transformations a little bit more obvious. So I'm going to put the exponential function first. And instead of writing it as x over 3, I'm going to rewrite that as 1/3 times x. And then I've got the little plus 2 at the end. So if you're thinking about our transformations that we have here, we have number 1, the x coordinate being multiplied by 1/3 here, or sorry, the x value being multiplied by 1/3, that's a horizontal stretch. And remember that for a horizontal stretch, whatever that number is in front of the x, that's what we'll be dividing every x coordinate by. So when I say that this is a horizontal stretch, this is a horizontal stretch by a factor of 3. We're going to take every x coordinate and divide them by 1/3, which is the same thing as taking every x coordinate and multiplying it by 3. So our graph will be 3 times wider in that horizontal direction. Then we're going to take our graph and flip it in the x-axis. So instead of curving upwards, it'll now be curving downward. And then finally, we're going to take that graph and shift it upwards by 2. So our graph will eventually be curving downward. And if we're thinking about in advance what we can expect for our domain and our range, we know that for the domain part of things, that the domain should be all real numbers. And I can predict what my range should be. Again, if I'm thinking about how this graph should look, the basic shape, e to the x, would be a graph that opens up and it has values for y values that are larger than 0. If you stretch it horizontally, that doesn't change what the y values are. Flipping it means that the y values will all now be less than 0. And now moving everybody up by 2 means that all of our y values should be less than 2. So I'm going to predict in advance here that I think my range should be all the values that are less than 2. And we'll circle back and see if I was correct on that. Now, one thing I do want to mention just about the graphing, and this is, again, comes back to what I said earlier about exact values versus approximate values. We know that the 3 points that are on the graph of e to the power of x are, of course, as always, 0, 1. We've got 1 comma our base, which is e. We've got -1 comma 1 over our base, so -1 comma 1 over e. And when I label my graph, those are the exact values that I'll be using. Those are the labels I should be using. If I decide to use my calculator to figure out roughly what e is equal to, 2.7-ish, I would be wrong if I labeled my point with 1 comma 2.718, because e is not the same thing as 2.718. E is close to this, but close to is not the same thing as exactly equal to. So when I'm graphing this, although I might use my calculator to figure out roughly where should the y-coordinate be on my graph, when I label things, I will be labeling them with their exact values. So let's start with this first one that I'll graph, which is y equals e to the power of x. I already know that I'm going to have that horizontal asymptote of y equals 0, so I'll fit that in. I've got the point 0, 1. I've got the point 1e. E is just a little bit shy of 3. And I've got the point -1, comma 1 over e. And 1 over e is about 0.37-ish. So again, just somewhere around a half. And then I know the basic shape is it's going to be exponential growth curving upwards. And on the left side, tapering off to that horizontal asymptote. I do just want to say one thing about my drawing skills here, which you have noticed probably that my drawings are sometimes a little bit wobblier than I might like. And there are things where maybe it might look a little bit misleading. If you're looking at this, it may look as though my graph is just about ready to cross the x-axis. But of course, we should know that for the exponential graph, e to the power of x, or actually any base to the power of x, has no x-intercept. This is not going to be crossing the x-axis. So although it might look like it, my graph here is actually just becoming closer and closer to that horizontal line of y equals 0, but it's not actually crossing it. So even though my graph might make it look as though it's about to cross, it is not. This is getting closer and closer to being horizontal on the left-hand side. All right, so now I'm just labeling my graph as y equals e to the x, and then I'm ready now to work on my first transformation. My first transformation, that would be the horizontal stretch. So again, I'm going to be taking every one of my x coordinates, and I'm going to be dividing by 1/3, which is the same thing as taking every x coordinate and multiplying by 3. That first point, 1e, take our x coordinate and multiply it by 3. That gives you 3. So 3e as our first point. 0, 1, the x coordinate is 0, so multiply the x coordinate by 3, it still stays as 0. -1, comma 1 over e, we are multiplying that x coordinate by 3, so we'll get -3, comma 1 over e. And we'll still have our horizontal asymptote of y equals 0. And that's, of course, because if you have a horizontal line and you stretch it horizontally, it will still be a horizontal line. It'll be just the same line as you started with. Stretching a horizontal line horizontally won't change its location. It's only the vertical shift that we'll do at the end that will change the location of this horizontal asymptote. So this is y is equal to e to the, and you could write this as x over 3 or 1/3 x, however you prefer to write it. Okay, so first transformation done. Second transformation is going to be my vertical flip. I'm multiplying all of my y coordinates by -1. So when I have my y coordinates, I'll have a y coordinate of -e, of -1, and -1 over e. And again, when I'm writing these out, I'm going to label them as 3, comma -e. I'm not going to be turning this into an approximate value using my calculator to express it as a decimal. I can use my calculator to figure out roughly where it is, or roughly what is -e. It's about -2.7. But when I label it, I'll be labeling my point as 3, comma -e. So now let's do that. Let's take all of our points and multiply the y coordinates by -1. So 3e is now 3 -e. 0, 1 is now 0, -1. -3, 1 over e is now -3, -1 over e. My horizontal asymptote will still be there, y equals 0. And now my graph, instead of curving upwards, will curve downwards. On the left-hand side, it will still taper off to that horizontal asymptote. And so there we go. There's our graph of y is equal to negative e to the x over 3. And the last thing that we were doing was the shift upwards. If we're looking back at our graph here, or the equation of it rather, the plan was to now do a vertical shift upwards by 2. And of course, if you're doing a vertical shift upwards by 2, the graph will go up, but the vertical asymptote, horizontal asymptote rather, will go up as well. So the original horizontal asymptote that we had was at y equals 0. We shift everybody upwards by 2. That asymptote is going to go upwards as well. We'll have the horizontal asymptote now being y is equal to 2. All right, so now let's just start labeling our points and plotting our points. We have 3 comma e, and we're going to take this point and move it upwards by 2, so it'll be between 0 and negative 1. So my point that I'll plot will be around here. And I'll label it as 3 comma negative e plus 2, because that's exactly what it is. We took the y coordinate of negative e, and then we added 2 to it. So the new y coordinate is negative e plus 2. That would be the exact way to label it. If you run this through your calculator, that's negative 0.7 approximately. But again, we're not labeling things with approximate values. We're labeling things with exact values. The next point that we had, 0, negative 1, adding 2 to the y coordinate brings us to 0, 1. So that point doesn't need to be labeled. Good, good. And we had the other point, which was negative 3 comma 1 over e, and we're moving that upwards by 2 points. So that means that it'll be somewhere between 1 and 2. That'll be where our final point is. And again, if we're labeling it, negative 3 for the x-coordinate, negative 1 over e plus 2, because we had the original y-coordinate was negative 1 over e, and we've added 2 to it, so it's negative 1 over e plus 2. If you run this through your calculator, that's about 1.6-ish, which again, somewhere between 1 and 2. We don't need to be perfectly accurate here. We just have to be reasonably close when we're doing our drawing. Again, the reason that we only need to be reasonably close is because we have our coordinates labeled. So there's no misunderstanding as to what exactly is it that I've graphed. So even if my point is not exactly at negative 3 comma negative 1 over e plus 2, if it's close to it and I've labeled it, then that's good enough. And now I'll just connect my points, tapering off to that horizontal asymptote. And this is the graph of y is equal to negative e to the x over 3 plus 2. And as I predicted, if we're looking at this graph, the final graph that we have here has only y values that are smaller than 2. And so not a surprise. This matches up with my range that I had predicted originally, that my range would be y values that are smaller than 2. Okay, so this one is just coming up with the equation. We're not actually going to do any graphing here. We have the function y equals half to the power of x, and we're going to shift it to the right by 1, then we're going to reflect it in the x-axis, then shift it down by 3 units. So if I were writing that equation, I would say number 1, we have half to the power of x minus 1, that's our shift to the right by 1. Reflecting it in the x-axis, that's a negative in front. We're multiplying this entire function by negative 1. And then shifting downward by 3 units, that would be subtracting 3. So my function that I have here should be negative of 1/2 to the power of x minus 1 minus 3. That would be taking my graph of half to the power of x, shifting it to the right by 1, flipping it, and then shifting it down by 3.